So the giveaway again for the Vidic is if you see triphenylphosphine, right? That's the signal that you're doing a Vidic reaction. If you see that triphenylphosphine um, molecule. All right, so it's a multi-step reaction, and it happens through what we call the illet. You can see the illet down here. So the illet it's a, a type of molecule where you have a positive and negative charge adjacent to one another. Sometimes you'll also see it referred to as a Zwitter ion, another German word. Right, sometimes you'll see it referred to as that, but it still means the same thing. You have a positive charge and a negative charge adjacent. So you have to, all the steps in the Vidic, the first steps get you to the illet. And then after that, that's when the illet reacts with the carbonyl. So we're going to talk about uh, how this works, right? We're going to talk about the mechanism for the Vidic. It's actually not that bad. Right, so the Vidic mechanism, again, the first step is dedicated to making the illet, right? So you have so the reagents are an alkyl halide, triphenylphosphine, and then a strong base. So normally what you do is you stir together the alkyl halide and the phosphine, and then you add in the base, stir that low temperature, and then you come back and pipe in or syringe in your aldehyde or your ketone, right? So you always make the illet first. So if we take, let me write this out. So we take triphenylphosphine, it has a lone pair, it's in group 5 with nitrogen, and we react that with a alkyl halide like methyl-bromide. Right, this part of the reaction again, I keep stressing that all these reactions, you might not know the reaction, but the concept behind it we've already discussed, right? So this is just a simple substitution. It's a SN2 type substitution, right? Where the phosphine comes in and attacks carbon, and you break the carbon-bromine bond, right? So what you end up with is a phosphonium ion. So now this is CH3. And then the bromine is just kind of forms a salt with that. Right. All right. So then in the next step, that's when you need the base. So I had potassium terbutoxide up top, but you really can use any strong base, but we'll stick with that one though. All right. So what that's actually going to end up doing is pulling a proton off a carbon. Right, so this is where your illet is going to come from. So I'm just going to pull off that one. Boom, like that. Give those electrons back to carbon. All right. So once you do that, right, that's when you have generated your illet. So now the illet is going to look like this. So it's P as positive, and then CH2 and that's negative. Right? So this illet is the reactive species, right? That's what's going to actually react with your carbonyl. Right? And again, this reaction is actually one of the easiest reactions I've ever done as a graduate student. You literally just stir your phosphine together with the alkyl halide, add in the base, go to lunch, come back, add the aldehyde or ketone, because it'll work on aldehydes or ketones. So the first part of the reaction is illet formation. And then in the second part of the reaction, that's when your illet is going to attack your carbonyl. Right? So if you have a carbonyl, aldehyde or a ketone, this doesn't work on acids and it doesn't work on esters, but it'll work on aldehyde or ketone. So if you have a aldehyde or a ketone, let me see if I can get this in here. All right, so here, let me just do, which one do we have up here? Okay, so here's my aldehyde. And that's negative and that's positive, right? So that carbon in the illet is going to attack your aldehyde and break the carbon-oxygen pi bond. Right, so you're going to end up with this intermediate that kind of looks like this. So this is O minus. That's H. And then you'll have a bond to this carbon over here. I'm just going to put the ethyl group like that. And then this is the CH2. Right, phosphorus is still positive. And then I'm just going to write out the hydrogens on that carbon. All right, so this come on, yo. All right, so this intermediate that you see, it doesn't stay like that, right? It actually cyclizes. So you go from this is called a beta-ene. Right, and that doesn't stay like that, obviously, because you got electrons around oxygen, and phosphorus and oxygen love each other. So oxygen is going to attack phosphorus, and then you end up with what's called an oxophosphatane. So let me draw that right quick. And then boom here, P. All right. Any questions about this so far? So now once that cyclizes, this is where your alkene is going to come from. How do you think that happens? So if I want to put a pi bond here, because that's where my alkene is going to come from. How could I do that from this intermediate?
Could you pull off a hydrogen?
Pull off a hydrogen. Only if you kept the other bonds intact. Sorry, I'm trying to do that. What you could do is collapse this down though. Right then, this is actually the driving force behind the reaction. Is if I take this CO bond and move it here, I take this CP bond and move it here, I'm actually going to get out, and I didn't write the name of this here. Oxophosphatane. So once I break that down or collapse it down, excuse me, you're going to get P double bond O. That's one of your products plus alkene. It looks like this. Right? So the formation of this phosphine oxide, that's what pushes the reaction. Because that PO double bond, you release a lot of energy by making that. Right? So that's the driving force behind the reaction is the formation of that phosphine oxide. All right. So once you get to the oxophosphatane, it's very rapid when that breaks down quickly to give you the alkene plus the phosphine oxide. All right. Any questions about that? All right. So that PO double bond, you get a lot of energy from that or release a lot of energy from that. And so that is uh, the driving force. That's what's pushing the reaction. So if you remember from Chem, Le Chatelier's principle, the more of that PO phosphine oxide you make, the more of the intermediate that's going to break down to generate more, right? So the more of that you make, the faster that intermediate is going to break down to try to keep up with that equilibrium. Right. So the Vidic happens again in two parts. It happens, you have the illet formation, which we have shown up top. And then in the second part of the reaction, you have the attack of the illet on the carbonyl. And that's where your alkene is going to come from. right, any questions? No questions. All right. That can be good or bad. In this case, I think it's bad. But when we start doing the examples, it'll make more sense. Another way to think about this, even if you don't know the mechanism, or you can't come up with the mechanism, there is a kind of, I don't want to call it a shortcut, but there is a way to think about this, right? If you look at your alkyl halide, right, and you look at the product, right, what did I lose from the alkyl halide to get to that product?
The oxygen.
Okay, so no, that's on the carbonyl. I'm talking about the alkyl halide right here. So what did I lose from that? You're right. I do lose the oxygen.
The bromine
You
and a hydrogen.
and a hydrogen. So one way to think about this is the alkyl halide minus HX, whatever your halogen is, and one hydrogen. And so the carbon that's bonded to the halogen, that's the carbon that's going to replace oxygen. So let me show you. I'll give you an example. So if I had an alkyl halide that looked like this, right, where it had six carbons, right, and I reacted this with, I'm just gonna do acetone, and then PPH3, and then a base. The product is going to be it's going to be this carbon right here. So I got two hydrogens on there. So it's going to be, if we subtract out HBr, what we're left with is CH. And so that carbon is going to be what replaces oxygen. Right. So when you think about the reaction, if you just want to predict the products, you find the alkyl halide and subtract out a H and whatever the halogen is from the carbon where the halogen is, that carbon is what you're going to replace oxygen with. That's a simplified way to think about it. Right? But you always replace the oxygen in the carbonyl, right, with the carbon of the alkyl halide that eventually is going to become your iller. So that's another way to think about it. All right. Any questions about that or about anything? All right. Again, you can do this on aldehydes or ketones. There are other methods if you want to convert an ester to an alkene. You can do it, but there are other methods for doing it. But this method is specific for aldehydes and ketones. So that's one reaction of carbonyls, and then the other reactions which are shown down below are hemiacetal and acetal formations, and those two kind of go together, right? The hemiacetal is a precursor to the acetal. So let me cut this out, and we're going to go through this mechanism, and then we're going to work through some examples. Just need to add a page. Oh, actually, I don't. You have to pardon my slow Wi-Fi. I just got power back like an hour ago. I don't know what happened. I think they were working on somebody else's power. And screwed mine up. All right. So a hemiacetal you make by reacting ketone or an aldehyde, doesn't matter, with one equivalent of alcohol. So in a generic sense, let me show you the generic version of this. Right, you have an aldehyde, and let's say you react it with some generic alcohol, right? What you're adding, this is an addition reaction. What you're adding is the alkoxy part of the alcohol. Right, and you also add in the proton. So you're adding both pieces of that alcohol across that CO pi bond. But the proton is going to add to the oxygen, and the alkoxy part is going to add to the carbon. So what you end up with in the product is so now this is OH, right? It's the same hydrogen that came from the hemiacetal. I'm sorry, from the alcohol. And then on this side, you have OR, whatever the alcohol is, whatever the R group is. And then the other CH3 that was already here is still intact. Right? You don't change that, right? So this again is it's an addition, and alcohol is your nucleophile, right? In most cases, when you're dealing with carbonyls, the carbonyl is going to be the electrophile, unless you're doing like a proton transfer with it. And if that's the case, then the carbonyl acts as a nucleophile by picking up the proton or a proton. But let's look at how this works, and then we're gonna go through both the hemiacetal and the acetal, and then we're gonna work some examples. So if I look at that first example where I have this ketone, I'm gonna draw that up like that, if that's okay. And I react that with 1 mole of methanol. All right, keep in mind, anytime I use an alcohol, that oxygen has lone pairs that it can donate. All right, so that's how I can say that the alcohol is nucleophile in this case. And really, again, going back to what I said earlier, all this stuff is just nucleophile, electrophile, or acid-base chemistry. That's all we're doing. So the arrows and all that stuff is all, we learned all that in part 1. All right. So what do you think is going to happen here? My carbonyl, keep in mind, my carbonyl has a huge dipole going this way. Let me get that arrow right. Big dipole, right? So that's partially negative, partially positive. So what do you think happens in the first step? If this is my nucleophile, and all your carbonyls react the same way with nucleophiles.
What?
Is that right? So the alcohol is going to attack the carbonyl, right? And then you're going to end up breaking that CO pi bond. All right, so all carbonyls will give you, if you reacting with a nucleophile, they all give you the same. Remember we talked about this with those Grignard reagents. They give you this tetrahedral intermediate. I'm gonna draw this up here. Oh, so the next step won't look so crazy. All right, so that's positive, and then I still have this ethyl group down here. All right, this tetrahedral intermediate is common for any carbonyl addition. You're always going to get a tetrahedral intermediate that either eliminates to give you the pi bond back, or you quench it with like a proton source or something like that. All right. So now here, all I need to do now is a proton transfer. So I'm just going to do this and that. Boom. It's all acid-base nucleophile electrophile chemistry. So I'm left with this. Right. This is what we call a hemiacetal. Let me ask the question. Is that proton transfer inter or intramolecular?
It's an intro.
It's intra, right? It's not, the proton is not coming from an external source, right? It's coming intramolecularly from another atom within the same molecule. So it's intramolecular. All right. That's your hemiacetal. If you want to make the acetal, you start with 2. If you can see right here, if you want to make the acetal, you start with 2 moles of alcohol instead of 1. And the starting point for the acetal formation is the hemiacetal. So if you want to make the acetal, then you start with the hemiacetal. So this, I'm going to start with what we have up here. Matter of fact, I'm just going to cut it and paste it. Come on. Paste that right there. Put this back up here. All right. So for the first step in acetal formation is proton transfer. Right. So you're going to actually take another mole of alcohol. All right. And you're going to pick up the proton from that alcohol. All right, so you end up with water, hydronium intermediate. So that's positive now. And then, sorry about that. That doesn't change. And then now you have that plus OCH3 minus, right? Because you took the proton from the alcohol. All right. And now this is a mechanism for the acetal formation, right? You have 2 possible pathways for this, the acetal formation, right? One is to just lose water and do like a SN1 type substitution. The other is to force water out using the lone pair from this oxygen over here, right? But I think for what we're doing, we'll just do it in an SN1 fashion, right? So if I lost water, come on, right? What I'll get, let me just move this down right quick because I don't want this to get cut off when I post the notes. Right, if I lose water, what should I get?
You're just you're gonna have the same molecule, but you just lost water. So
Right, but what should it be positive? Is it a carbocation?
I would think so. Yes.
Yeah, it's a carb. That's what I was getting at. I should get a carbocation if I lose water, and I do. Right, there's a plus charge on this carbon, and then the OCH3 minus that's still kind of hanging around. Now that can react with that carbocation. Right, so now this comes here, boom. Right, reacts with that, and so now that's where I get my acetal from. All right, so the acetal is a derivative, of a hemiacetal. So the hemiacetal you make by using 1 mole of alcohol plus a ketone or aldehyde, and then the acetal you make by using 2 moles, right? And you can see the difference in the two compounds, the two products, right? So the hemiacetal, you only have 1 mole of alcohol, so you add 1 alkoxy moiety, and then in the acetal, since you started with 2 moles of alcohol, you can see now you have 2 alkoxys attached to that carbonyl carbon. All right, any questions about that? All right, let me switch to a different handout. And here, perfect. All right, so now let's see if we can apply some of these reactions. So let's look at the reaction at 3 o'clock. I think this is probably the easiest out of all of them. Right? What reaction is that? I think that's the only one I don't have labeled. I kind of gave it away. But what reaction is that, and what's the product? So I have alcohol, and I'm reacting it with a base followed by an alkyl halide. Don't all answer at once now. So I have an alcohol here. I'm going to treat it with sodium hydroxide. What do you think happens when I do that? So this is a Williamson ether synthesis. Right? You have an alcohol, you react it with a base, and then an alkyl halide, and then you actually end up with an ether. Can you see that or no?
Yeah, we can see.
Hmm? And does anybody have a question about the actual reaction, right? We talked about this before, where you take the alcohol and deprotonate it to make it a better nucleophile, and then you react it with the alkyl halide like a SN2 type reaction. All right. Then try to do that. All right. Any questions about that? Y'all are extra quiet on a Friday. Usually you're more excited than that on a Friday, but it is Friday. Maybe you'll be more excited at 10:30. All right. Let's look at the next reaction because this is a sequence of reactions. And the only thing I haven't talked about off that other handout is the Amine formation, but we can do that here. All right. What about the next reaction right here? What is the chromic acid going to do to that alcohol? So anytime you have, sorry about that, chromic acid in the presence of an alcohol, right? That's one of our methods for alcohol oxidation. So if it's a primary alcohol, we're going to oxidize it up to an aldehyde, excuse me. And if it's a secondary alcohol, we'll oxidize it up to the ketone. So what's the product from that first reaction? Right, the alkene, we're not touching that. All these reactions are going to be specific for that alcohol. So don't get sidetracked by that alkene. Is that what I should get if I oxidize this alcohol up using chromic acid?
Yes.
All right, and then in the second reaction, what do you think? I kind of gave it away here that it's acidic. So what's the final product going to be? Because that's the aldehyde is not the final product. That's just the product from the first reaction.
Would it be an alkene?
Yes, it'll be an alkene. So acidic is a way to turn carbonyls into alkenes, right? And then this would be CH2. You see what I did? All I need to see is if we're not asking about the mechanism, all I need to see is the alkyl halide. And if I subtract out an H and the halogen, what I'm left with, that's what I'm replacing oxygen with. So if I take the CH3 Br and I take away, this is bad, this is not math per se. If I subtract out HBr, what I'm left with is a CH2, and that is what's going to replace oxygen. right? Even if I don't know the mechanism, when I see the reagents, I can recognize them and say, oh, this is Vidic. So this is going to turn carbonyl into an alkene. All right. Let's do the top reaction. What will potassium permanganate do to that alcohol? It's another way to another oxidant. All right. Potassium permanganate, we talked about this Wednesday. It's like a superoxidant. So you got a primary alcohol. The potassium permanganate is going to actually take that all the way up to the carboxylic acid. Right? It's not going to stop at the aldehyde or the ketone. What about the second step? What should the final product be here? If I take a carboxylic acid and react it with an alcohol,
Would that alcohol be replaced with the CH3?
you're close. You're close. So when I add an alcohol to a carboxylic acid, the actual part of the alcohol that gets added is the OCH3, so the alkoxy part. But that's a good answer. So I'm gonna take this acid and then right, so I end up with the ester plus water. So the potassium permanganate, that's the oxidation part. And then the alcohol part is the transesterification. All right. If you haven't already, you probably should make some flashcards with these. Make some flashcards with these reactions on it. All right. Let's look at the last reaction. What's the product from the first part?
Would it be an aldehyde?
Yeah, you're gonna get an aldehyde as a result of that first reaction. The second reaction, if I have a primary amine and react it with an aldehyde, we're going to talk about that. We'll probably wait and talk about it Monday. But if I have a primary amine and I react it with an aldehyde or a ketone, I get out what's called an amine. Right? Are y'all doing that in Organic 2 lab, the amine formation?
We didn't have lab yesterday, so he might have had us doing that, but we didn't have it.
Okay. So I'll just show you the product, and then I'm not gonna have time to go through how it works, but I will go through that on Monday. So you get an amine where the oxygen is replaced by nitrogen, and then plus water. I think the mechanism is on this handout, or maybe on a different handout. Yeah, it's on a different handout. That's all right. We'll talk about the mechanism on Monday. But the amine formation, that's a reaction that is pretty common with aldehydes and ketones. You have a primary amine plus an aldehyde or a ketone, that's going to give you an amine. All right. Any questions about those reactions? I know it seems like a lot, but you got to practice them. You got to get reps, and more reps. So that's what we'll do on Monday. We'll cover the reactions of carbonyls with amines. We're going to cover that, and then we're just going to work through some more examples. All right. Any questions about anything? No?
Yeah, I just need to go review.
Yeah, it's gonna take some time to go back through those reactions and the videos and the section, because that if you look in the syllabus, every reaction, the section where it can be found in your book is listed in the syllabus. So definitely you gotta see it, touch it. I only got 15 people in class today. That's ridiculous. The hardest section, and we only got half the class here. It's not good. All right. If there are no other questions, I'm gonna stop I'm gonna stop the recording. Yeah, definitely. I'm gonna stop the